Hi, today we want to discuss module on chapter 3, Gravitation. So look at the first part, 3.1. It is about Newton's universal law of gravitation. So I hope you already watched the videos. So what is stated by Newton's universal law of gravitation? Okay. Gravitational force F is directly proportional to the product of mass of the object and inversely proportional to the square of distance between them. And we get this formula, F equivalent to G m1 m2 divided by r square. And F actually is gravitational force between the objects. G, capital G, universal gravitational constant. So this is the value. M1 mass of the first object, M2 mass of the second object, R is distance between the center of the object. So I hope you understand or you know this formula. So this is what concluded by what is stated by Newton's law of gravitation. Okay, next we want to discuss about factors that affect gravitational force based on the formula. We also know that there are two factors that affect gravitational force. The first one is mass of the object m and distance between object r. So for the case of mass of the object, as the mass increases, gravitational force increases, because earlier we discussed that F is directly proportional to m1 times m2. Okay. Second one, as the distance increases, gravitational force decreases. We also discussed that F is inversely proportional to r squared. So that's the reason why this happened, or the factors that affect gravitational force. Okay, look at uji kendiri 3.1.1. So for number 1, given the value of G, universal gravitational constant, so you use the formula that is stated by Newton's law of gravitation. So you solve the problems, or you can complete the table below. If you look at the first example, given m1, m2 and r, so you want to find what is F. So you use formula G m1 times m2 divided by r squared. So you just substitute the value of m1, m2 and r in the formula, then you get the force 1.44 times 10 to the power negative 8 Newton. So you can continue to complete the table below by using the same formula. Sometimes they give you m1, r and f, they want you to find m2. So you just use the formula and solve it mathematically. So I think this one you complete it by yourself. Okay, next question, number 2. So we have two objects with mass 3.5 kg are placed 4 meters from each other. Calculate gravitational force between the objects. G are given. So what you do, you just list down all the information given, like M1 3.5 kilogram. Okay. And then this one is same mass. So M1 3.5 kg, M2 3.5 kg. So placed at 4 meters from each other, meaning R is equals to 4 meters. Okay, so you just substitute, so you get the answer 5.11 times 10 to the power negative 11 Newton. So as you can see from here, if the mass of both objects are smaller, like 3.5 times 3.5 here, so you see the value of the force that act between the two objects is very, very small, like 5.11 times 10 to the power negative 11 Newton. That's the reason also why we cannot feel the force of attraction between us and other objects, like between you and your TV, or between you and your table or laptop. Okay, there's always force of attraction, but the value is very small as compared to gravitational pull of Earth. That's the reason you cannot feel the force of attraction. Okay. Okay, number 3. Number 3, now we look at given for number 3, mass of Earth and mass of Moon. This one involve large object. if the gravitational force between the Earth and the Moon is given, what is distance between the Earth and the Moon? Okay, so you solve the problem using the same formula, F equals to gm1 m2 divided by r squared. So you list down first, what is m1, what is m2, what is r. Okay, then you can, this one need you to find r, so given is F. So you just rearrange the formula so that r will become the title of the formula, then you substitute all the formulas. So you get r equals to 3.8 times 10 to the power 8 meter. Okay. Okay, for part B, bahagian B. So, bahagian B ni, part B. Okay, relationship between gravitational acceleration and universal gravitational constant. One is small g, one is capital G. Okay, now using the information below, complete the diagram to derive relationship between small g and capital G. Means gravitational acceleration and gravitational constant. So capital M is mass of the Earth, small m is mass of object, r is distance between center of Earth and center of the object. Always center to center because this one involves large object. Okay, based on Newton's second law of motion, so we have F equals to mg, gravitational force from the Newton's second law, that is F equals to ma. So object that fall down with acceleration due to gravity, so the force that act is equivalent to mg. So this one is first equation. So based on the Newton's universal law of gravitation, so we get F equivalent to gm, m, capital M, divided by r squared, because involving Earth and object, and another object. Okay, so what we do now, gravitational force is equivalent to, from the second law, so this one are equal. So equation 1 and equation 2 are equal. So mg equals to gmm divided by r squared. So you can cancel the small m. So you get small g equivalent to gm divided by r squared. So this is the formula that relate gravitational acceleration and also gravitational constant. Okay, g. Okay. Okay, now look at number 2. Okay, from number 2, the value of universal gravitational constant and mass of Earth are constant, state factors affecting gravitational acceleration. So from the formula here, we can see the value of g and m are constant, meaning gravitational acceleration just depends on r. So the only factor that affect here is distance between center of the Earth and the object. When we discuss about object and the Earth, like satellite and the Earth, for example. As the distance increases, gravitational acceleration decreases. Meaning if the object is far from the center of the Earth, the gravitational acceleration is smaller. Okay, now you can see how the value of small g, gravitational acceleration, change as the distance between two objects change. So you can see here, capital R is the radius of the Earth. So you can see from 0, 0 means at the center of the Earth. So center of the Earth, gravitational acceleration equals to 0. So meaning from center to the surface of the Earth, gravitational acceleration increases. So you can see g directly proportional to r. Until reach the surface of the Earth, there is distance equivalent to radius of the Earth. The value of g equivalent to, from the same formula that derived before, equivalent to gm divided by r squared, meaning g is universal gravitational constant, m is mass of Earth, r is radius of Earth. And when you calculate by using the information needed, so you will get the value at the surface of the Earth equivalent to 9.81 meter second negative 1. Okay, that one we always use that value for calculation. So you can see as the object move further from the surface of the Earth, so meaning the value of r increases. So what happened? Value of small g or gravitational acceleration decreases. So from here, the relationship is small g inversely proportional to r squared. Okay, so meaning the further the object from the Earth, the smaller the value of gravitational acceleration. So that's explain the shape of the graph. Okay. Okay, so we have the second uji kendiri 3.1.2. Okay, so you look at question number 1. The diagram shows object A on the surface of the Earth and B at height h from the Earth. R is radius of the Earth, small r is the distance of the object from center of the Earth, and m is mass of the Earth. So you can see we have object. The object may be a satellite, for example. Okay, based on the information given, derive gravitational acceleration in terms of g, m, r, and h. Okay, so look at A for object A. So for object A is at the surface of the Earth, meaning the distance between object A and center of the Earth equivalent to radius of the Earth. Then we can write r equivalent to capital R, radius of the Earth. So from the formula we get small g equivalent to gm divided by, not small m here, capital M, capital M. This is wrong already, capital M. So divide by capital R square. So meaning g multiply mass of the Earth divided by radius of the Earth square. So you'll get the answer. So make correction. Don't just copy down. So this one should be g capital M divided by R squared. For object B, which is at height h from the surface of the Earth, so the distance between the center of the object to the center of the Earth should be r, radius of the Earth, plus h. So h also must measure from surface to the center of the object here. Okay, so r equivalent to r plus h. So we get g equivalent to gm. Here also is capital M, mass of Earth, divided by r plus h squared. So we get the value or the g, the small g, derived in terms of capital G, capital M, and capital R and H. Okay. Part B given. Mass of the Earth given, radius also given, universal gravitational constant is also given here. So calculate part 1, the value of gravitational acceleration of object A. So we use the formula G equivalent small g, gravitational acceleration equivalent to G, capital G, times mass of the Earth divided by radius of the Earth square. So we get 9.81 Newton per kilogram, or 9.81 meter second negative 2. Same unit. Okay, part 2, the gravitational acceleration, the object B, is at 3.5 kilometer height from the surface of the Earth. Remember, we always use SI unit. So you can see the final answer always stated in SI unit. So that's why the height here in kilometer, you must convert to meter. So it becomes 345 times 10 to the power 3 meter. So use the formula here. G equivalent to capital G times mass of the Earth divided by R plus H. So M must be mass of the Earth, capital M. So do make correction for this one. Okay, number 2. Diagram shows 3 satellites A, B, C, different height, okay, from the surface of the Earth. So we want to calculate gravitational acceleration, x on the object, A, B, C, okay. So information needed also given here. G, mass of the Earth, capital M, radius of the Earth, capital R, okay. So you use the same formula at certain height, meaning the total distance between two objects, you must take R plus H, radius of the Earth plus H. Okay, so you solve this one. You can take the final answer, then you can do it later for this one. Okay, part C. Part C is about centripetal force in motion of satellite and planet system. So what is a centripetal force? We discussed that for any circular motion, there must be force that we call centripetal force that always directed toward the center of the object. If we discuss about Earth, center of the Earth, so centripetal force. A force that makes body to follow a circular path with direction always towards the center of curvature. Okay, so we have centripetal force F equivalent to mv squared divided by r, where F is centripetal force, m is mass of the object, v is linear speed or orbital speed, r is radius of the circle. Okay. Okay, number 2. State the factors that affect centripetal force. So there are factors like this: mass of the object m, linear speed v, and radius of the circle. So from the formula, F equals to mv squared divided by r. So as mass increases, centripetal force increases. As speed increases, centripetal force increases. As radius increases, centripetal force decreases. So you just use the formula to explain factors that affect centripetal force. Okay, look at number 3. The diagram shows a satellite move in an orbit around the Earth. The satellite always experiences gravitational force that acts towards the center of the Earth. The gravitational force acts as centripetal force to the satellite. So actually the centripetal force equivalent to gravitational force of the Earth. Okay. By using force formula, F equals to ma, and centripetal force, derive formula of centripetal acceleration. So we have formula, the first formula we use from the Newton's second law, F equals to ma, and centripetal force, F equals to mv squared divided by r. So you just compare these two formula, so you will get A equivalent to v squared divided by r, or from here equation 1 equals to equation 2, so you can cancel small m. So you get A equals to v squared divided by r. So A known as centripetal acceleration, and this v is the orbital speed or linear speed of the object. Okay, now we go to the Uji Kendiri 3.1.3. Okay, number 1. The diagram shows a stone with mass 0.5 kg tied to the end of a string and spin horizontally with radius 30 cm and speed 4 meter per second. A, on the diagram, mark an arrow direction of centripetal force X on the stone, labeled with F. Okay, so you can see, you can mark in the direction is towards the center of the rotation, meaning to the hand along the string. Okay. Okay, part B. Then we go back to what we have. Maybe we missed something below here. Okay, the first part we have discussed. Part A just mark. Okay, so the next part will be part B. Okay, 1B. Calculate the centripetal force. So use formula F equals to mv squared divided by r. Okay, so the m is 0.5, and the v is 4. R equals equivalent to 30 centimeters. So you need to convert to meter. So you will get the force equivalent to 26.67 Newton. So you want to calculate the centripetal force. So A equivalent to V squared divided by R. Same thing, the V is 4. R equals to 30 cm. You convert to meter. So you will get 53.33 meter second negative 2. Okay, question number 2. A bottle with mass 0.3 kg tied at the end of a string and spin horizontally with speed 5 meter per second. Centripetal force produced is 10 Newton. A. What is the radius of spinning orbit? So meaning you just play with the formula. Let R become the title of the formula. So you solve it, you will get 0.75 meter. Okay. Part B, if the speed increases to 15, what is centripetal force X? So you just use the same formula, now the same mass, and then the speed increases to 15, so become 15 squared divided by radius that we get from here, 0.75, so 90 Newton. Okay. Okay, part D, we want to determine the mass of the Earth and mass of the Sun. So using the Newton universal law of gravitation and centripetal force and the given information, complete the diagram to derive mass of Earth formula. Okay, so we can use this situation. So I hope you are familiar with this symbol. Capital M, mass of the Earth, small m, mass of the Moon. V, linear speed of the Moon. The linear speed is this value. Okay, the speed that keep changing. Direction every time the object orbiting around the Earth. Okay, small r, orbital radius of the Moon from center to center. This is the orbital radius. Period of the Moon around the Earth, meaning one complete revolution or one complete circle of motion. So the time taken, we call it period of the Moon around the Earth. Okay, now distance travelled by Moon in one complete circle is equivalent to circumference of a circle. This is from maths. So you have 2 pi r. So meaning the linear speed of the Moon equivalent to distance divided by time. The distance travelled for one complete circle is 2 pi r. The time taken for one complete circle also is period t. So we get V equivalent to 2 pi r divided by t. So from the Newton's universal law of gravitation, we have discussed that F equivalent to G m divided by r squared. And the centripetal force F equivalent to mv squared divided by r. So these two values are equal, so meaning Gmm divided by r squared equals to mv squared divided by r. So you can cancel the small m and cancel one r here. So you will get v squared equivalent to Gm divided by r. So what you do, from this formula, you substitute the value of v here. V equivalent to 2 pi r divided by t. So you substitute into the v here, and then you open the bracket, it will become Gm divided by r equivalent to 4 pi square r square divided by t square. And then you rearrange so that mass of the Earth, capital M, become the title of formula. So it becomes 4 pi square r cubed divided by gt squared. So from this formula, actually, we have derived one formula in order to calculate mass of the Earth, M, capital M. Okay, look at uji kendiri 3.1.4. Okay, number 1, the diagram shows a satellite at 356,830 km height from the surface of the Earth. Calculate mass of the Earth if the period of orbiting the Earth is 86,400 seconds. Given radius of the Earth and g, the gravitational constant. Okay, you solve it. Period r, you substitute the formula, so you get 3.79 times 10 to the power 27 kilogram. Okay, so you want to calculate also the same formula used. Want to calculate mass of the sun, you also use the same thing, but period now is the period of Jupiter. It depends on what object you discuss. And r here, small r, is distance between center of Jupiter to center of the Earth. And then you can calculate mass of the Jupiter. Sorry, mass of sun. So you substitute all the values, so you will get the answer here. Okay, so that's all for today. Thank you.